Okay, we're here to talk about section 8.2, testing a claim about a proportion. Now, before you go through this section, I had started recording a video for 8.1 basics of hypothesis testing, but really it's just a decent amount of terms and stuff, and the calculating is in the future sections, 8.2 and 8.3 that we're going to cover, one this week and then one next week. So what I did instead is I posted the link to the MyMathLab video inside of the homework. So if you start the homework, there's a 24-minute video where they go over some of the different terms that will be addressed in this video. So I would suggest that you go back and watch that video and or read section 8.1 so you understand some of the terms like p-value, critical value, type 1 error, type 2 error, null hypothesis, alternate hypothesis, things like that before watching this video. Also, the first questions on the homework assignment for this week are going to be based on those terms as well. All right, so in this section we're going to look at a procedure for testing a claim made about a population proportion. In the next section we're looking at claims about means, so it's going to be pretty similar. So we're going to do hypothesis testing using both the p-value method and the critical value method, which were talked about in that section 8.1. And we're going to look at using confidence intervals. So you can use these methods with claims about population proportions, probabilities, or percentages. So there are different methods here. First, we're going to look at using the normal approximation method to a binomial. That works pretty well. And then right at the very end, we're going to look at some other methods called an exact method for binomial probabilities. But anyway. All right, so our objective is to conduct a formal hypothesis test of a claim about a population proportion. Some notation: N is your sample size or number of trials. P is your population proportion. That's what we're going to use in the null hypothesis. P hat is your sample proportion. And then Q is 1 minus P. Some requirements: you have to have a random sample. You have to have a fixed number of trials in your distribution. The trials have to be independent. Each trial must be either a success or a failure, and the probability of success has to remain the same in all the trials. And then to be able to use this normal approximation method, N times P and N times Q both have to be greater than or equal to 5 to do this normal approximation. And then we have U is NP and sigma is in square root of NPQ that we did back in section 6.6. Here's a calculation to find a z-value. We aren't going to need that because we're going to be using StatCrunch. Again, p-values we're going to find using StatCrunch. Critical values, you actually could use the z-score table that we had before to compare to critical values. So that's in Appendix 2 in the textbook, or if you just Google search a standard normal distribution table, that will pop up. So you can compare to those critical values. That was in one of the last homework assignments that we did also. But actually it's on page 379 in the book, so you guys could go find it right there. Now, the thing here is that the confidence interval method is not equivalent to the p-value and critical value methods here, so you might get a slightly different conclusion. The reason for that is based on how the standard deviation comes about with these different methods. So the recommendation is to use a confidence interval to estimate a population proportion, but use a p-value method or critical value method for testing a claim about a proportion. So we did confidence intervals in the last chapter. Now for means and for standard deviations, those methods are actually identical, but for proportions they are not. So claim most consumers are uncomfortable with drone deliveries. 1,009 consumers were asked if they are comfortable with having drones deliver their purchases. 54%, or 545 of them, responded with no. Use these results to test the claim that most consumers are uncomfortable with drone deliveries. We interpret most to mean more than half or greater than 0.5. So, do we meet the requirements? The 1,009 were randomly selected. There's a fixed number of trials that fit into two categories. They're uncomfortable or not. N times P is greater than or equal to 5, and N times Q is greater than or equal to 5. In this case, our N is 1,009, our P is 0.5, and our Q is 0.5. So those numbers are both much bigger than 5. They're 500. So we are good to do what we want to do. So we can do the solution by the p-value method or the critical value method. So they did some stuff with TI-8384, and we can do that exact same stuff with StatCrunch, and that's what we're going to do here. So we have 1,009 trials, and 545 successes. So let's go to StatCrunch. We're going to do stat. We're going to do proportion stats, one sample, with summary. We had 545 successes out of 1,009 observations. Our hypothesis test, our null hypothesis here is that it's 0.5, and our alternate hypothesis is that it's greater than 0.5. I'm going to hit compute. So you can see I got a p-value of 0.0054 and a z-stat of 2.55. So let's go back and take a look and compare with what they got. You can see they got those exact same values, 2.5499 and 0.005386. So solution by the p-value method. So we did technology. So basically what we're looking for, we're going through the steps. The original claim is that most consumers are uncomfortable with drone deliveries, and that claim can be expressed in the form P is greater than 0.5. The opposite of that claim is P is less than or equal to 0.5. Solution by the p-value method. The expression P is greater than 0.5 doesn't contain equality, so that becomes our alternative hypothesis. The null hypothesis is that P is the fixed value of 0.5. So our problem setup is P equals 0.5. P is greater than 0.5 is the alternative. That's what I used when I set up StatCrunch. You have to choose the significance level in step 4. So alpha equals 0.05 is very common. So what you're doing in that case is that if you are doing the p-value test, what you're looking for is a p-value that is less than that 0.05. We also got the test statistic, which we got 2.55. They're calculating it by hand here. We had that from StatCrunch, 2.55 z-stat, p-value 0.0054. So by the p-value method, since we got 0.0054, that is less than the 0.05 that we were looking for. So we're in really good shape. So actually, let's skip to step 7. Our 0.0054 is less than the 0.05 that we had for alpha, so we can reject the null hypothesis. If you wanted to look at it from the critical value method, actually we should go ahead and finish this, step 8. So since we rejected the null hypothesis, we support the alternative hypothesis, and we can conclude that there is sufficient evidence to support the claim that more than half the consumers are uncomfortable with drone deliveries. Now the only way that this looks a little bit different when you use the test values instead of the p-values is what you do then is you compare the test statistic 2.55 to the z-value that gives you the right amount out in the tail. So that comes to looking at that table, the normal table, the one that we looked at in the last homework assignment. And on there, you will find that a z-value of 1.645 corresponds to having alpha of 0.05 in the right tail. So if your value is higher than that 1.645, then you're in good shape. Okay, I actually went and opened up this table. I'm not sure where these page numbers they have before were, but anyway, this is Appendix 2 in the text. It's on page 701. And we're looking in the right tail. We want an area of 0.05, which means to the left we would want 0.95. And you can see that's actually listed down here on the table. If I want 0.95 to the left, my z-score is 0.1645. That's where that came from. But the other thing you could do is just kind of look around in the table and see, oh, 0.95, that's 1.64, 1.65. Oh, it's halfway in between. It's 1.645. That's where that one came from. There's another table if you wanted, in the left tail, say I wanted 0.05, you could see that's negative 1.645 for a score. So that's where they're getting those critical values to compare to. So our value of 2.55 is greater than that critical value, which puts us way out to the right, which puts us in a good place. And then actually 2.55, you can see 0.9946. And if you do 1 minus that, you get our number that we were comparing to, which is 0.0054. That's our p-value. So those p-values are not like magical numbers. They're just 1 minus the area values that are on here, at least out in the tail. That's what they come from. Okay, let's continue. All right, so we have completed that problem. We ended up on that one rejecting the null hypothesis and concluding that most consumers are uncomfortable with drone deliveries. And we did that with both the p-value and the test statistic. Now, what if you wanted to do this with a confidence interval? That's something we could have done in a previous section. If you set up a 90% confidence interval using a p-hat of 545 over 1009, we could have done that in section 7.1. Again, using StatCrunch, we could build a confidence interval, and it would be between 0.514 and 0.566. So we'd be 90% confident that our true value of p lies inside of there, which again seems to support the claim that more than 0.5 consumers are uncomfortable with drone deliveries, since 0.5 is not in our confidence interval. But again, a hypothesis test is the right thing to do in this case, and these are not identically calculated. So, all right, so sometimes you might not be given the number of successes. So for example, a study of sleepwalking or nocturnal wandering was described in Neurology magazine, and it included information that 29.2% of 19,136 Americans have sleepwalked. Well, you might have to do a little calculating and realize that that means it's 5,588 just by multiplying. So once you've got that, we could do another test, and in this case, we want to see the claim is that fewer than 30% of adults have sleepwalked. So we want to do this again at a 0.05 significance level. So going through the steps, do we meet the requirements? Yes, it's a simple random. Yes, we have a fixed number of independent trials that fit in 2 categories. Our NP and NQ greater than 5 is definitely both satisfied. Our N is 19,000, our P is 0.3, and our Q is 0.7. That's 1 minus P. So we get huge numbers for that. So our original claim is that P is less than 0.3. The opposite is P is greater than or equal to 0.3. P is less than 0.3 doesn't contain equality, so that becomes our alternative hypothesis. And it's what we claimed originally. And then P equals 0.3 is our null hypothesis. We're going to use a significance level of 0.05 again. So again, we can set this up in StatCrunch the same way that we did before. We have 5,588 out of 19,136. Let's see if I remember those numbers. I almost certainly will not. So we're doing proportion stats, one sample with summary. You have 5,588 out of 19,136, I think. Yeah, I did it. We're looking at a hypothesis test this time. The null hypothesis is that it's 0.3, and we want less than that. So compute. We immediately see that we got what we wanted in terms of a p-value, 0.008, and we were looking for anything less than 0.05. So we have succeeded our hypothesis. We are able to reject the null hypothesis in this case. But let's go ahead and go back through the steps over here. Again, they're going through calculating the z. We're not doing that. So our p-value is 0.008 because that's less than or equal to our significance level. We reject the null hypothesis. So since we rejected the null, we support the alternative, and we conclude that there is sufficient evidence to support the claim that fewer than 30% of adults have sleepwalked. Now, if you wanted to do that with a test statistic, you would be comparing that negative 2.41 to the value that would put 0.3 in the left tail. So if you want 0.3 in the left tail, you would go look at this chart and find about 0.3 for area. That would be somewhere in between these two values, which would be negative 0.52, negative 0.53, somewhere in there. And you can actually see that we're way, way below that negative 0.5. We were actually at we wanted 0.05 again. So sorry, we were looking for negative 1.645 again, and we were at, on our StatCrunch, we were at negative 2.41. So we're way below what we needed to be for a z-stat also, if you wanted to do it that way. It's just two different interpretations of the same thing. The p-values are a lot easier given that the technology is doing it for us, but sometimes the question will ask you to do it with the test statistic, I think. But if we can get p-values, it's way easier just to compare that to our alpha. Okay. So there is a way to do this exactly. So using an exact method, you look at the sample size, the number of successes, the claimed value of the population proportion, and we find p-values using technology. And basically what we're going to do with this exact method is we're going to find the binomial probabilities. So again, they want us to take 10 randomly selected couples. They each have a baby. 9 of the babies are girls. Use a 0.05 significance level to test the claim that with this method, the probability of being a girl is greater than 0.75. We do not have to do the NP and NQ check here because we're going to do this exact. We're not using the normal approximation. So our hypothesis, null hypothesis, is that it's 0.75, and we're looking for an alternative hypothesis that it's greater than 0.75, this proportion. So what we're going to do is use the binomial probability and find the probability of getting 9 or more successes among 10 trials. And if that probability, given a 0.75 assumed population probability, if we end up less than our 0.05 for probability, then we're good. You can see they did this in a TI-84 here and found the probability to be 0.244, which is not less than 0.05, and therefore this failed. So we are not able to reject the null hypothesis in this case. So how would you do that in StatCrunch? Well, Stat Calculator's binomial. We had 10 trials with a probability of 0.75, and we want the probability of greater than or equal to 9. Compute 0.244. Right, so if we had 100 trials and 90 girls, then we would get what we wanted. But the deal is, we just had too small of a sample here to be able to verify this. There's still a 24% chance that we could just end up over in this tail part. So basically it's saying our sample's not good enough if we get 9 or 10 girls out of this. It's just not good enough to be able to reject the null hypothesis. I don't think we'll do a whole lot with exact methods. They have a method in here for slightly improving this method, where on a right-handed test like we just did, you do the probability of 9 or more like we did, and then subtract 1/2 the probability of getting exactly 9. So like on that case, we would then subtract half of this number. So we would do greater than or equal to 9 is 0.244, and then subtract half of this, so that's like 0.09. That would still not be good enough to avoid rejecting the null hypothesis in this case. But alas. Okay, I think that should get you through most of the homework between the combination of how doing these calculations we showed in StatCrunch here, and then watching the other videos / reading section 8.1 so you understand some of the terminology. So I'm going to stop this recording, and I'll see you on Thursday.